Shalom class, welcome again to our second lesson of the day. In the morning we discussed about now the diamond as one of the allotrope of carbon. This time round we are going to discuss on now the graphite. Just to start now, I would like us now to look at some properties of the graphite and actually differentiate between these two allotropes. We have these two major allotropes of carbon, the diamond we discussed in the morning, and now we are also going to discuss now this graphite as the second allotrope of carbon. Now, just to start, we can say something about this graphite and say that now graphite has hexagonal structure or has hexagonal layers. They have hexagonal layers. And one thing that you need to know about this one here, these hexagonal layers, for example, look at this structure here. Look at this structure of graphite. For example, this is your hexagonal layer. This is the first layer. This is the first layer. I have another layer below here. That actually looks like this. And this other one. So when you look at this layer here, this is the first layer. Hexagonal has now the 6 sides. These are 6-sided figure. This is the first hexagonal layer. This is the second hexagonal layer. Between a carbon atoms of these hexagonal layers, we have a covalent bond that is bonding this carbon atom. But this one here being one of the molecule, this one also being another molecule, these molecules are held together by this weak force of attraction. These molecules are held together by this weak force of attraction, like this. This is what we have. So look at this one now. From this particular molecule, the first molecule and the second molecule, or the first layer and the second layer, there is this bond that actually holds these molecules together. This bond, we call it weak van der Waals forces of attraction. Weak van der Waals forces of attraction. Weak van der Waals forces of attraction. I hope by now you know that now weak van der Waals force of attraction, these are force of attraction between the molecules. It's also called intermolecular force of attraction. This is the first molecule, the second molecule. Between these two molecules, the first layer and this layer here, they are held together by these weak van der Waals forces. And these weak van der Waals forces is a force that you can easily break them. And because of this force here, this layer and this layer can easily slide over each other. So we are saying that now not in diamond, but graphite, these layers are held together by, or these hexagonal layers are held together by weak forces of attraction, which actually makes them to slide over each other because it's a weak force of attraction. So we say that the layers slide over each other. The layers slide over each other. And because of this one, we are saying that now the reason as why these layers slide over each other is that now they are held together by weak van der Waals force. The reason here is because the layers are held together by weak force of attraction. The layers are held together by weak forces of attraction. or some people call it weak van der Waals force of attraction. Forces of attraction. So the force of attraction that is holding these layers and these layers together, they are very weak, and because of that one, these layers keep on sliding over each other. So there are some physical properties here that you need to understand. So when look at this one here, this one we have a single carbon atom bonded together to another carbon atom. So meaning that now this carbon atom, each of these carbon atom is bonded to 3 other carbon atoms. So we are saying that now in graphite, each carbon atom, each so in graphite, each carbon atom is bonded to 4, not to 4, but to 3 other carbon atoms. 3 other carbon atoms. So what does that one tells you? And now, out of the 4 valence electron, only 3 of the valence electrons are used in bonding. So we are saying that now, because one carbon here is bonded to this other carbon, to this other carbon, to this other carbon, and to this other carbon. This is also another carbon here. Though the bond between this one here and to this one here is a weak force, but now this carbon atom has been bonded to 3 other carbon atoms, and this one tells you that now out of the 4 valence electron, only 3 of them are used in bonding. So we are saying out of the 4 valence electron, out of the 4 valence electrons in carbon, only 3 valence electrons are used in bonding. So this is what we are saying, that now out of those 4 valence electrons, out of the 4 valence electrons in carbon, only 3 valence electrons are used in bonding. Only 3 valence electrons are used. Only 3 valence electrons are used in bonding. So meaning that now the fourth one that remains, the fourth electron that remains is what you call the localized electron. The fourth one that remains out of the 4, where after removing the 3 which has been used in bonding, then the fourth one that remains is what you call the localized electron. So the remaining electron, the remaining electron is delocalized. The remaining electron is delocalized. And because of this one, we can actually say this very important thing, that graphite is a good conductor. Graphite is a good conductor of heat and electricity. That graphite is a good conductor of heat and electricity. What is the reason behind this? I'd like us now to discuss on the reason behind this. The reason behind diamond, or not diamond, but graphite being a good conductor of electricity is that graphite has a delocalized electron. So due to the presence of delocalized electron. Presence of delocalized electrons. due to the presence of the localized electron. And because of that one, you can say that graphite is a good conductor of electricity. So in the morning we were discussing about diamond, and we said that diamond is a clear, transparent, and shiny crystalline, but this is different for graphite. Graphite is opaque. Graphite is opaque. Graphite is opaque. I think in primary school you discuss about opaque. These are now the ones that do not allow a light to pass through them. The materials that do not allow a light to pass through them. A good example is a block, and others. Now, having known this one, we can also discuss about the melting point, and it has relatively low melting point, relatively low melting point, and the reason here is due to the presence of weak van der Waals forces. Reason is due to, this is due to presence of weak van der Waals forces. Presence of weak van der Waals forces. Not only that one, can also say that it has a density of 2.3. It has a density of 2.3 gram per centimeter cubic. It has a density of 2.3 gram per centimeter cubic. Now, having known these properties, I'd like us now to look at the uses of graphite. Uses of graphite. Uses of graphite. Uses of graphite. Number one, graphite is used as a lubricant. Graphite is used as a lubricant. Graphite is used as a lubricant, and the reason behind now graphite being used as a lubricant, the reason behind now the graphite being used as a lubricant is that now graphite is used as a lubricant, and the reason behind the graphite being used as a lubricant is because it is soft and slippery. It is slippery in nature. It is slippery in nature. The second use of graphite is that it is used as an electrode. It is used as an electrode. I want to discuss this one in electrochemistry, especially in Form 4, or even I think you must have talked about this one in your previous class, in the fifth topic of Form 2, the effect of electric current on substance, where you used graphite as electrode. So graphite is the most preferred electrode, especially when we are dealing with now those solutions, those electrolytes. We are joining now the two solutions. We are using graphite as electrode. Now, what is the reason behind this? The reason as to why graphites are used as an electrode. Number one, we said graphite is good conductor. It's a good conductor. That's why we use it as an electrode. And number two reason as to why we are going to use this one here, it is inert. I think inert means unreactive. Inert means unreactive. Inert means, so these are the two reasons. Is inert and it is good conductor, and because of that one, graphite is used as an electrode. The third use of now graphite, the third use of graphite is used in making of lead pencils. Used in making of lead pencils. It is used in making of lead pencils, and the reason here, in most of the exam, seen a question where the students were asked to give a reason why not diamond, but graphite is used in making of lead pencils. So we can say the reason as to why it is used as a lead pencil, we can say that graphite, I'm sorry, it's not diamond, it's graphite. So we can say that now graphite is soft and slippery. Graphite is soft and slippery. Soft and slippery, and also it's black. Soft and black, hence easy to write on a paper. Is a soft and black, hence easy to write on a paper. Hence easy to write on a paper. It is soft and actually black, and because of that one, it can easily write, or hence easy to write on a paper, and because of that, it is used as, or in making of these lead pencils. They are actually soft and black, and hence easy to write on a piece of paper. So when you are told actually to give a reason or explain why graphite is used in making of, how graphite is used in making of a lead pencils, we can say that graphite being soft and black, it is easy to write on a piece of paper, and that is actually the reason. So these are three major uses of graphite. This one will lead us now to the next allotrope that I'm not going to discuss today. I just mentioned it. This is now the next allotrope here, is called fullerenes. Fullerenes is also called Buckminster. There are some people call it Buckminster. They are also called fullerenes. Buckminster or fullerenes, these are the synthetic allotrope. These are the synthetic allotrope of carbon. These are the synthetic allotrope of carbon, and they take different shape, e.g. spherical shape. They take different shapes. They take different shapes, e.g. spherical shape, and other shapes. So these are some things that now we need to understand about these allotropes of carbon. Next thing we are going to discuss about other forms of carbon that I'm going to just mention for today. Then I'm going to discuss them in details in our next class. Other forms of carbon. These are actually non-crystalline forms. Other forms of carbon. These are non-crystalline or impure forms of carbon. And one of this one, we call it amorphous carbon. I call this one amorphous carbon. Amorphous carbon, this is impure form of carbon. Amorphous carbon is the impure form of carbon. This is the impure form of carbon. E.g., a good example here. Example we are going to discuss here. We have charcoal is one of the example. We have coke is another example. We have soot is another example, and others. The charcoal, coke, soot, coal, mention others that I've not mentioned here. These are just some few examples I'm mentioning for you. These are now the impure forms of carbon. We are going to discuss their properties and details in our next class. Shalom. Subscribe to my YouTube channel and continue learning from me. It's your teacher, Mr. Emmanuel. Thank you, and may God bless you.